Our last speaker will be Mako Bates, who's going to tell us about choreographic programming.
Hello, I'm Mako Bates. I'm here to tell you about choreographic programming that is efficient in terms of its communication overhead, that's portable in the sense that you can use these techniques in your favorite language, and that is census-polymorphic, which is a property that I'll get to in the second half of my time. So I'm going to spend a few minutes setting the stage, making sure we know what choreographic programming is and why we want it, and how other people have worked on that idea. And then I'll explain conclaves and multiply located values, which are our solution to one of the fundamental problems in choreographic programming. Then we'll talk some about our implementation strategy, how that interacts with conclaves and multiply located values. And finally, we'll get to census polymorphism, which is one of the keys to allowing real code reuse in choreographic software. So writing systems of concurrently executing programs is hard. We've got 3 small programs up here that are designed to run simultaneously and in communication with each other. And we need to ask questions like, what does this system of programs do? How might it fail? Does it do what it does efficiently? We can make reasoning about systems like this easier for ourselves by instead writing just one program that describes everybody's behavior simultaneously. That's the idea of multi-party programming, the particular flavor of which that we're talking about today is choreographic programming. In choreographic programming, you write one protocol from a third-person omniscient perspective. It's exactly like you're telling a traditional Alice and Bob story. Characteristically, we don't have distinct send and receive operations. Those are 2 sides of the same coin. We call that unified operation communicate. We write it often with a little squiggle arrow. So on the left here, we say Alice communicates X to Bob, who binds it as Y. During compilation, or at some other point in the process, you're going to do endpoint projection, which is where you extract an individual party's behavior and an implementation of their behavior from the global choreography. So on the right, we have the projections to Alice and to Bob, respectively, of this one communication operation. For Alice, that projects as send X to Bob. For Bob, it projects as receive Y from Alice. The advantage of writing your software this way is you get some static safety guarantees. You'll never have to worry about deadlocks. And when a party receives a communication, they don't need to worry about where in the program the sender was when they sent it. So it's an easy way to write your software. It makes it easier to reason about. Here is a more involved pseudocode example that shows off those same features. We've got one thread of action in which 3 different parties are taking actions at different times. On line 4, we see that unified communication operator with the squiggly arrow again. On line 2, the argument this function requests is a list of requests located at the client. And something very similar happens implicitly on line 8. The type checker or the compiler or somebody is going to have to infer that handle R double prime is something that's done by the processor. So this is pseudocode. Our goal is to write actual software like this. There are some existing systems you can use. So Coral is very nice. It is tightly integrated with the Java ecosystem. Pirouette has a similar level of integration with Coq. Those are expressive and efficient, but they need their own compilers. If you write your software in Coral, you'll have some Java code in there, but you have to use the Coral compiler. There are also some intermediate systems. So Corix and Chlor augment their host language's syntax with macros and compiler plugins. But what we want is fully library-level choreographic programming. And HasChor showed that that was possible at ICFP a couple of years ago. It's very easy to use. You start a new Haskell project, you import HasChor, and you write your choreography. What you lose is the efficient and explicit communication that ought to be characteristic of choreographic programming. The reason why this is hard, the thing about the choreographic programming that's not trivial, is managing knowledge of choice. So in this diagram, we're supposing that Alice has some located Boolean called X, and Bob's behavior needs to depend on that X. So when Alice looks at X and chooses which of these branches to take, Bob needs to know that choice and take the same branch. And right away, we have to ask, does anyone else need to know? In this particular case, yeah, actually everyone needs to know, because if we imagine projection to some third party, such as Carol, then they need to have either receive an integer from Bob or receive a string from Bob, and that needs to be well defined. Coral and a lot of prior systems use a select and merge strategy in which there's a designated communication operator just for managing knowledge of choice. And if the user makes any mistakes in their knowledge of choice management, that's detected during endpoint projection. But if you're doing library level choreographic programming as an fully embedded DSL, then your endpoint projection is going to happen at runtime. And we don't want runtime errors. So HasChor's strategy was to implicitly broadcast the guard of every conditional to everyone, which works, but it's not efficient because not everybody needs every single guard. The first step towards improving on this is to take a census of the participants. So the census is what we're calling the list of parties who are present to participate in a choreography or in some part of a choreography. Some prior works have had these as part of their type system and use them to manage function declaration and function application. Our formalism, lambda C, also annotates case expressions with their own censuses because it's using the census as part of the knowledge of choice management strategy. Here's what effect that has on a broadcast situation. We go into the conclave with Alice and Bob, so the census is now just Alice and Bob. When Alice broadcasts X, well, actually, she's just sending it to Bob. Carol's not inside the conclave, she doesn't get it. And here's how we use conclaves and broadcasts to do efficient knowledge of choice. On line 3, our census is explicitly client, server, and backup. The first thing that happens is on line 5, client sends request to the server. And then down on line 8, we're going to want to branch on the nature of the request. Is it a get or is it a put? But only the server and the backup need to be participating in that branching operation. So on line 6, they enter a conclave. That entire do block that starts on line 6, the census is just server and backup. So on line 7, when we broadcast the request, that doesn't go back to the client. They don't need it. They're going to skip this whole block. And then the server and the backup can branch on line 8 as described. But what do we actually get when we leave the conclave? What is the type on line 6 of the bound variable response? In our earliest versions of Chorus, we just required that conclaves return multiply located values. The details of that turned out to be buggy, and also we can do better than that. I got to skip over some of the story of exactly why, but a conclave has to return a multiply located value. Specifically, the conclave operator takes a choreography with some census and lifts it to a choreography with a super census, and it wraps the return value as a multiply located value owned by the subcensus. We've seen a couple instances of located values so far. They're just values or variables annotated with an owner. Multiply located values work the same way, but they have a list of owners. The critical thing about a multiply located value is that there's only one value. All of the owners know and agree on that one value. So this gets us back the efficiency and explicit communication that we hope for in choreographic programming. Expanding on the earlier diagram, we assume that Alice owns some X. Inside the conclave, she can broadcast it, so now she and Bob both have it. They can branch on that together, and whatever the return value of this conclave is, outside the conclave will be viewed as a multiply located value known to everyone who was in the conclave, Alice and Bob. Carol never participates in that. So our formalism combines multiply located values and conclaves to make an efficient and intuitive and also completely type-directed knowledge of choice strategy. It's a lambda calculus. It has normal properties for lambda calculus like preservation and progress. And endpoint projection is well-defined and sound and complete for all well-typed programs. So your network semantics never get stuck. We get some other stuff from multiply located values. We can reuse knowledge of choice in sequential conditional blocks. And we also get really concise expression of active replication. But finally, this is really easy to implement. Let's talk about implementation strategies. In a sense, choreographies are just another DSL. Where the rubber hits the road is endpoint projection. HasChor did this with monadic effect handlers, but you don't need that. You don't even need monads. Any form of dependency injection should suffice. What we're doing is we say, choreographic programming with such and such census, that's an interface. A particular choreography is a consumer of that interface. And you do endpoint projection by providing an implementation of the interface that implements the specified party's behavior and skips over everybody else's actions. There'll be some core operations kind of at the foundation of that interface. You're not set in stone exactly what those are, but I do recommend these as a good choice for your 4 foundational operators. We've talked about broadcast and conclave. Congruently, explicitly does active replication. There's a couple different options for how to do it, but you'll want to have some way of doing that. And locally handles side effectful computation by one party at a time. In multi-core, we're using freer monads. In chorus, we're using traits, the trait system. In choreo-TS, we're using polymorphism in a fairly straightforward way. If your language can do dependency injection in whatever form, you can probably do choreographic programming. And insofar as your language can do type-safe dependency injection, you can probably do type-safe choreographic programming. But other than intuitive and efficient knowledge of choice management that's statically checked by the host language's type checker with recyclable embodiment of knowledge of choice as data, what do these techniques get us? Well, obviously, they get us everything that the host language gives us. This is real, compilable, executable Haskell written using the multi-core library. And it contains a bunch of stuff that I didn't have to build. We've got monadic bind, lambda case, do notation. We've got Haskell's clear distinction between pure and impure code. I got all that for free. And there's a few other functions in here that I haven't described yet. On line 11, the gather function, and parallel on line 9. The second argument to this function on line 4 is a faceted value. These are also things that we get quote unquote for free in Haskell. And they're really important because they're what's doing census polymorphism in this example. So let's talk about that. Modern concurrent protocols have lots of participants. I found some examples where they're running them with thousands of participants. And really, once you get up to 4 or 5, you don't want to have to rewrite your software every time somebody wants to add one more participant. So looking at the sequence diagram here, there might be thousands of servers, or it might be the case that there's only the one server called primary. This diagram is ambiguous about that, and that's exactly how you actually write it in multi-core. We have the traditional concurrent programming operators scatter and gather, and then a third one, parallel, is how you do handle request in the middle of this diagram. In order to give those things sensible types, we need some new data types. So faceted values are very much like multiply located values. They accept that their contents diverge. Every owner of a faceted value will have their own value of that value. Quires are static vectors indexed by parties. So the opposite of a faceted value is actually a located quire. And as I mentioned, we get this for free in Haskell. For free in the sense that we could have left it out of the library and people would have been able to write it themselves. Not free in the sense that you'd first have to write this stuff. So the point of this code block is not to learn anything profound by understanding it, but rather that this is a transparent and completely type-safe helper function that rests on top of the core API I was describing earlier. Down at the very bottom, I don't know if everybody can see, we have this type P indexed. That's a party indexed lookup table from type level parties to runtime values. The types of those values depend on the party you're looking up. Sequence P sequences over parties. It takes a P indexed and a P indexed whose values all have a common monadic structure, and it sequences them together in that monad. So this is great. We can do this stuff very nicely in Haskell, but it's too good to leave in Haskell. We got to do this in all the other languages. So in your language of choice, what you'll probably do is you'll add the key operators that you want for census polymorphism as little black boxes in your core API. A lot of languages aren't going to have enough type-level hijinks for the sequence piece strategy. So in Chorus and Choreo-TS, we hard code fan in and fan out. Fan in is a loop function. It takes a body that returns a located value with invariant owners, and it loops over a list of parties and wraps up all those return values as a quire. Fan out is basically the same, except that the body returns variables located at the indexing parties, and they get wrapped up as a faceted. But if your language can't actually encode those, you can do the even more specific operators, scatter, gather, and parallel. You lose a little bit of flexibility in each of these different options, but at this point, we don't actually have a case study showing why you would need the full power of the sequence piece system in the real world. So, kind of wrapping things up, you can do choreographic programming in whatever language you want, using conclaves and multiple located values with census polymorphism. You won't have to worry about your concurrent systems deadlocking or other kinds of miscommunications. You can handle all kinds of different configurations of participants. In the paper, we've got a couple of case studies. A lot of the details are in the appendix. My next 3 slides are QR codes for each of our implementations. So multi-core is our Haskell implementation. You can pull it off of Hackage right now. There's going to be a version 2. So if you're interested in what might go into that, you can come to my dissertation defense a week from tomorrow. Chorus is our Rust implementation. On crates.io, it's chorus_lib. It has really nice tutorial-style documentation. Choreo-TS is our TypeScript implementation. You'll have to install it from GitHub right now. I mentioned that different languages give you different things for free. The thing you get for free in TypeScript is really good type-level expression and handling of subset and membership constraints. So that aspect of the system actually works out much cleaner in Choreo-TS than what we were able to do in the other languages. Thank you again, and thank you to my co-authors up here. My name is Mako Bates. I am looking for a job. Don't forget to fight fascism, and we have time for some questions.
I have a question, Mako.
Yeah.
You mentioned that there were several different options for the congruently operator. Can you tell me about some of those?
Yeah, so in all of these systems, we have a really minimalist set of core operations. You could fluff those up a little bit, and that would save you some layering work on top. In the case of congruently, it's kind of a weird odd one out. The obvious other option would be a simple naked or unwrap operator that just takes a multiply located value known to the entire census and turns it into an unlocated value. For version 2 of multicore, we're going to have an even more bare bones system where the entire notion of a located value kind of disappears. But I don't think we have time for that in this session. Okay.
So on one of your like code snippet slides, I saw that you had like an example with a conclave where you sort of explicitly write down what the census is for that conclave.
Yep.
Are there any ways to sort of automatically synthesize this, or have the compiler tell you that, hey, you've added someone to the census that's like not necessary, or like this is, you know, bigger than it needs to be, or like if for example I explicitly write conclave server backup and client on line 6, is the compiler able to help me out and say client doesn't actually need to be here?
No, it won't. And depending on the kind of performance or other property that you're trying to get out of it, you don't need it to. We could put together a situation where there'd be a performance cost to including people erroneously in the census.
Well, like when you broadcast, you have to send it to everyone in the census, right?
Yeah. So if you're doing a broadcast, in practice, the actual point-to-point communication or multicast is its own conclave with a broadcast that we build them all out of. So broadcast is not, when you're actually writing a choreography, you might not be using broadcast.
I see, okay.
But yeah, that's a good point.
I think we're going to have to take the last question offline just for time, but let's thank Mako again.